What? No, you didn't send me any requests.
It's on the top of your screen.
Oh, okay.
Ignore that. Just deny something.
Okay.
Okay, so the recording has started.
Yeah, I'll just put the workspace in the chat. So Python101, and yeah. Why can't I do it? Oh, now I can do it. Cool.
There's a few people here. If you got other friends who might want to join, please tell them to do so.
Yep. There is the workspace in the chat, so if you guys could download it and open it in your machines, we'll give you a couple of minutes to do so. Wow, not here. How do I start from a slide? I feel like 70-year-old now. Oh, slideshow from the current slide. Okay. Let me know in the chat, guys, if you're done more or less with downloading and setting up your workspace. I'll be back in a minute. Okay. How are people doing with the workspaces?
Some are done. Probably waiting for other people. A bit. Okay. 2 people have said done.
By the way, if you have any questions from the last couple of lectures, then please let me know. Okay, cool. I don't know why it shows my bar, but okay. Let's start. So in this lecture, we're going to talk a little bit about functions, recursion, and handling errors, and importing in Python. Functions will take the lion's share of today's lecture. So for now, you should all know how to do the user input and output and how to print stuff. Also understand how to use variables and what are the types like strings, integers, floats. You should also be able to compare different values. So if they're equal, if they have the same type, if they have the same ID, so if they occupy the same space in memory. And also a bit about for and while loops to do things multiple times and repeat things. And finally, something about lists, which are our first data structure, so our first collections of lists. So firstly, let's consider this print statement. So print is actually a function in Python. So it's something that does stuff. We give it an input and it does something with it. In our case, it will be printing things to the console. So mathematical definition of a function is that it takes an input and usually gives us an output if the input is defined for that functions. We can consider it as a black box. So basically, it might we might not really know what happens inside them, but we just care about the input and output. For example, f(x) equals 2x is a function. Yep, and they always, most of them, the mathematical functions, always produce the same output given the same input. All right, so functions in Python are slightly different, but very similar to mathematical functions. So they can say take a number and do something with it, and here we have a nice template. So this is how we define functions in Python. We first use the def keyword, then we do my function, then we pass in the arguments that the function will take. Then it will do something with those arguments, and then we'll return a return value, not exclusively the argument. Some functions do not return anything. They are called void functions, and they just do not have a return value. All right, functions in Python. Same slide. Okay. Can you think of any functions we have encountered so far? So this is, for example, the double function. It just doubles the number x and gives out the output, the result of the function. Okay. The other one is, for example, say hello function, which would take a string, an element, a name, and it would just print a message, hello something name. This is the example of the void function. So the function that doesn't return anything. It's not really equivalent to a mathematical function. Okay. This function actually doesn't take any arguments. It sort of behaves like it would, but it actually accepts a user input in the middle. So the greet function just doesn't take any arguments and doesn't return anything. So printing is not returning. So you cannot use the value, let's sort of print it by the function. You would have to have a return statement at the end of the function. Right. Another function is, for example, summing three numbers. So we take three arguments and just return the sum. So functions are very, very useful when you want to do something repeatedly. Okay, thanks, Seb. So if you want to do something repeatedly, if you want to make like a black box, some sort of abstraction that would help you to, well, work with your code, somehow divide it into smaller blocks. And these can potentially be messy with input and output if you don't take care about the input and output types. Yeah, and they can be thought of as many programs inside your bigger code. So they are a bit independent. Yep. One more important remark is that you can treat your whole program as a small main function. Right? Okay. Another function is the increment function. So this function will just increment the value of x. But let's have a look, how does it work in our workspace. Okay, increment x. Okay, and now print, let's say we have counter equal to 0. And we print counter. We also print counter plus 1. Sorry, counter increment. Okay, and let's have a look what it prints out. So it increments the counter. But what happens to the counter itself? It still stays the same. So this actually tells us a very important thing about integers in Python, because they are immutable. So here, this call doesn't really change the value of x we passed in. This is some sort of local x that will be just returned. So if you would repeatedly call increment counter, then it would just start from 0, increment it to 1. You would have to like repeatedly call it within nested brackets, like increment counter. Yep. Then it would do it double. Okay. Coming back to the slides. Yep. So you can see what it does. All right. So now we did this. So we have to consider the local x we're talking about, and this is called the scope. So inside the function, variables have different scope. So they can refer to different things. Okay. A bit more about the structure of the function. So please have a look for a minute. I'll be back in a minute. Okay, I'm back. So every function has a definition, a name, an argument, then a body, and then a return statement, right? So these elements are essential for a function. Yep. And here is a function call, which is name and greet. Okay. So now let's go to the exercises. And let's define the Marco Polo function. I'll define it as a play until loss function, and then I'll leave you guys to define it as a play once function. So Marco Polo repeatedly, right? We print, or we actually, let's say t equals input Marco. And now if we can use a while loop, for example, inside this function. So while true, we do t input, and we do if t equals to Polo, then we do, well, then we do nothing. So if it's not equal to polo, then we break. And that's basically the body of the function. And now to make it work, actually, okay, true, colon. So now to actually play the game, we have to call this function. Hello. So we do it here. And we do polo. Yep, polo. Gummo doesn't work, so it terminates. Okay. How about you guys now implement a version that just plays once, so without the while loop, but it has to print some, let's say, message to the user that he answered correctly or not. Yeah, I'll give you a minute for it. If there are any questions about functions so far, please do not hesitate. I have my second laptop open, so.
Sorry, what do you want us to do again?
So I want you to define a function that will play Marco Polo game. So Marco Polo game is just that we're printing Marco and we want the user to type in Polo.
Yeah.
Yep. And if he or she doesn't type Polo, then we just print something saying, oh, it's a wrong answer. It should be Polo.
Cool.
Okay. Anyone wants to maybe paste their code into the chat or share how they did it? Mm-hmm. Nice. I love the oopsie one. Oh, we just wanted to play once function, so we don't have to call the. Oh yeah, so we don't have to call it a rep, but this is just a naming convention. Yeah. Well, but yeah, it's a nice implementation. Okay, cool. So if you guys already have it, then let's go for the second exercise. So in this case, there are two approaches. You can either convert the input to the string and just loop through it and add numbers, or you can repeatedly divide them by 0 and use the modulus operator. I'll give you guys 2 minutes for this one. It's a bit more tricky. Okay, let's go for this one. So some digits. And we accept the number n. So we go, let's say we do a while loop and we will keep the track if n is greater than 0. We also have to have a result variable, which at the beginning will be 1. And we go from result plus equals n modulus operator. So what stays after the division by 10, right? And then we divide n by 10 with a whole number division. So this is just dividing the n by 10 without any decimal point. Without anything after the decimal point. Okay. Now we do. Now we return result. All right. Some digits. Yep. So we get 10 as required. Okay. Now, number 3. So some functions can take in objects, which means data structures. In our case, it will be a list. And they can modify them and actually return them modified. Here you have 2 implementations of the function that does the same thing at the first site, but it actually has a different outcome. Does any of you have an idea why is the difference? I can scroll up. So you can unmute yourselves or just type it in the chat. What might be the cause of difference in output? So the difference is here. Anyone has an idea why one function actually doubles the given list and the other one doesn't? It's quite a simple thing. Okay, so the cause is that here we're looping through abstracted out element from the list. So this is local for the function. And here we're accessing the elements in the actual list. So here Python will create a copy and just modify the elements. And here it will actually access the elements inside the list and modify them. Such modification is called a in place algorithm. So in place. And it's actually a very common method in many computational techniques. So you just give it an input and it modifies the input, but doesn't really return it. You just have the modified input at the end.
Sorry, can I say something? For the example above, I use the same code as you, but I'm getting an error, and I don't really know why.
What's the error?
It says type error. So I'm not sure if I'm entering the wrong number, but I'm entering, I don't know.
Type error. Well, you can paste your code into the chat and we can try to tackle it.
Yeah, sure.
you don't accept you don't have arguments in your function. You should have.
Yeah, I should put yep. That's so silly. Okay, cool. Yeah.
Does it work?
Yeah. That makes sense. Yeah, of
Cool.
course.
Let's tackle the last function, which is a simple search. So we are given a list of elements and a element, and we have to return whether the element A is in list L. So we don't want anything fancy. We just want to scan through the list. So a for loop might be helpful here. If you have any questions so far, then you can unmute yourself. All right, I'll start with this function. And we first loop through the list L. And now if lm equals to A, and we return true, otherwise if we went through the whole list, then we have to return false because the element was not found. Yep, and we can call this function on an example input. Okay. A list here, and we're searching for element 7, then it's not there. Otherwise, we're looking for 3. It's there in the print. Jupyter notebooks will usually just print the last return function on last returned value on default. So if we want all the values returned, then we have to do print. Yep. Okay. Coming back to the slides. Let's keep those. And we go into recursion now. So recursion is the ability of functions to call themselves in some cases. The most popular one, the most popular example will be a Fibonacci sequence. So given by this formula, and it calls itself. So it calls itself on a smaller input. With recursion, we have several cases. So there are base cases, which should be finite. So there should be several of those at worst. Usually there is one or two. And there are recursive cases, which call the function itself. And to assure that the function will terminate, which means that it won't call itself constantly, we have to, at least in a soft sense, so well, not scientifically, but at least have a feeling that the input will decrease and reach the base case at some point. So in this example, we have n, and it will go down by 1 in this call, down by 2. So we will eventually reach either 1 or 0. Yep, and this is the example of recursive Fibonacci sequence. So we can return the nth number in the sequence by using this function. So here we check whether the input is 0 or 1. We can also assert. I don't know whether we did assert, but I'll do it in a minute. We can assert, which is assume that the input is positive, and if it's less or equal to 1, then we will return 0 or 1. Otherwise, we call function again, and it does the same job. Yep, base cases, recursive calls. We have to be careful if they terminate, because otherwise we have something like recursion depth exceeded. If we just go too deep with function calls, and it just terminates the code with error. Okay, we'll do this in a minute. Coming back to the workspaces. So I was talking about the assert, so I'll just do an assert very shortly. So assert keyword is just an assumption keyword. So if we say assert something is greater than, let's say greater or equal to 0, then it means that we expect the input to be greater or equal to 0. Right, and now if n is smaller or equal to 1, then we return n. Otherwise, we return the sum of last 2. Yep, and we can do, for example, fib of 13 or 10. Yeah. All right. Now let's consider some. Yep.
So with assert, like if you left it out, wouldn't n being less than or equal to 1 cover that? Like it wouldn't have run without. Yeah.
It would, true, but there is no such a thing as minus 10th Fibonacci sequence term.
Right.
So it would return minus 10. If we do like minus 9 here, for example, it will just shout at us that we have an assertion error. And assertions are usually very useful if we want to track whether our code behaves the way we want it to. The other way is to return some value that signifies an error if we don't want the code to terminate. Depends if our goal is to terminate the code or not.
All right. Can I ask one more question? You know, in the previous example, the one above, when you was talking about why is there a different result between using the element and using the for loop? I missed out because I was working on the other code. Can you just explain quickly why there's a difference?
So here we have here Python copies the elements in the list and just doubles the copy. And here we're accessing the actual elements in the list, so the actual physical memory. And that is why it doubles. Yep. So when I was talking about the scope, so that names of variables have a different meaning inside functions, lists behave a bit differently. So we can actually modify them inside functions, which might sometimes be useful if you want to double a list without creating a new list. Okay. So maybe let's give it a shot and write a factorial function, which is recursive, so it will call itself. And yeah, I'll give it 2 minutes for this one. And if anyone can paste their code, that would be great, so we can analyze. Any ideas how to call the function inside itself for the factorial function? If you know what the factorial is, but I guess you do. So factorial of n is equal to n times factorial of n minus 1. Okay, I'll start with this one. If anyone wants to paste their code, then be fast. So we start with the n, right? And now we have to check the base case, which is if n is smaller than, say, for example, 1. Then we return 1. So factorial of 0 is defined as 1, which is a small exception. Well, okay. Give me a minute. Okay. Otherwise, we return the product of n and factorial of n minus 1. Okay. And we can call factorial, for example, on 7. Factorial on 0. But if we call it on a negative number, this is the importance of assertions, because yeah, it's not defined for negative ones, right? Also, if we would actually check whether it's equal to 1, not smaller than 1, then this would just run infinitely, because it would call itself until we hit the recursion error. So we were just calling constantly factorial of n minus 1, and we were not reaching 1 because we are already in the negative numbers. Therefore, we get a recursion error. So maximum recursion def exceeded. Well. Cool. I can leave it here and just comment it. Oh, it's still, oh yeah, because, sure. All right. Now maybe exponentiation. It is really similar. At least one version is really similar to the factorial function. So give it a thought for 2 minutes, and then I'll code it up. So this function will take in two arguments, a to the power of n, right? And now, if n is equal to 1, then it's one of the base cases, so we just return 1. Otherwise, if n is equal to 0, elif, then we return, well, 1, because anything to the 0th power is 1. And else, because we should also assert that n is positive, or non-negative, otherwise. Yep. And then we call the function again. So it will be a times expon of the same a, but n minus 1. You can also, there is also a more efficient way to do it that utilizes less calls to the expon function. I'll do it in a minute, but here you can see that there will be approximately n calls to the expon function, right? So if we would want to exponentiate something to the 7th power, then we would call this function 7 times. There is a more interesting way of doing it. Call it log expon. And now we have the same base cases. But now we also consider whether n is divisible by 2. So if it's not, then we will have a temporary value here, which will do log expon of a and divide it by 2, but with the whole division. And we would just return temp times temp. If it's non-divisible by 2, so it gives the remainder of 1. Then we also have the same temporary value here. And we do temp times a. Yep. Okay. And we can print, let's say 3 to the 7th, and print the log expon 3 to the 7th. And something went wrong. What is that? If you guys see any bugs, then let me know. Okay, n is 1 here. When n is 1, we should return a. And it's also a case here. No, still no. Okay. Whenever it's 1, then we return a. When it's 0, we return 1. When it's divisible by 2, then we return. Oh, okay. Yeah, it just took the log function, log expon. Yep, and it gives off the same result. to compare the number of calls, for example, to this function, we can print an exclamation mark in one of them and print, let's say, a star. 1. And let's do it for a slightly bigger number, so let's let it be 20. Yeah, so we can see that we have approximately 20 exclamation marks and just 5 asterisks. So there are less repetitive calls. It's a nice consideration if you care about the efficiency of your code, to see if there are any nice properties that you might use to make your code a bit more efficient. Okay. Does anyone know Euclid's algorithm to compute the greatest common divisor of two numbers? Was it greatest common divisor, I think? Yeah, Euclidean algorithm. So it's probably the most well-known recursive algorithm out there, and it allows us to calculate the greatest common divisor of two numbers. Okay, let's give it a shot. I'll just remind myself in the notes what was the actual equation. Okay, so definition of GCD of A and B is basically if B is 0, then we that's a base case. Therefore, we just return the first number. Otherwise, you return GCD of B and A by B. Yep. And we can check if it works correctly. 7 and 1. 8 and 5. Yep. And print the 8 and 4. Yep. So this is GCD, one of the famous recursive algorithms. It's more than 2,000 years old, so quite interesting. If you guys look for more examples, then please visit the webpage in the workspace. And there you have a bit more involved examples like towers of Hanoi or recursive data structures, which we'll cover later on. But there are also more exercises on recursion itself. All right. Now, coming back to the slides. Let's do a short comparison between recursion and loops. So when we want to use loops to do something, they might be a bit more difficult to write. Like if you imagine Marco Polo done recursively, then instead of a while loop, I would just constantly call Marco Polo if the input was Polo. So it will be a bit more easier to read. Recursion is also a bit closer to the actual mathematical definition of most of the functions defined in Python. But on the other hand, loops are actually the way computer understands those commands. You need to be careful with base cases, the same way you need to be careful with loop conditions. So you need to make sure that a loop condition will be broken at some point or satisfied at some point. The same way you need to assure that your input will finally reach the actual base case. Recursion is usually slower, so when people do some competitive programming and things like that, they tend to prefer loops instead of recursion. But if you don't care about efficiency that much, then recursion is way more readable. Not all recursion is slower. There is something called like tail recursion, which I will not delve into, but it's a bit more efficient than regular recursion. Yeah, that's reversed. Okay, reversing a list. So how would we do a list reversal with loop first? So let's do list reversal. And first the loop case. And we pass in a list, and we start from a for loop, for example, for I in range. And we will start from the last element of L. The last element is at length -1, and we'll go to the -1th element, which is not included, so to 0, and we'll decrease by -1 on each iteration. We also need a result variable. We'll not make it in place, we'll just return a new list. First we declare it as an empty list, then we do append. Yep. And we will append, well, something that's at the ith position. And we return res. So this is the loop case. And recursive case. With a list. So first, we'll just take the last element of the list, right? Which is at the position -1. Put it in the list. We can actually prepend it, and then we do ref recursive on the on what it's left. So we already took the last element. So now we can take the other ones. So we call it on a part of a list, which is up to len -1. There are different ways of implementing this algorithm, but this is one of them. Not very beautiful, but it is what it is. And now we can compare if they give out the same output for the same list. Do they not? All right. So you see, I have forgotten about the base case. What is the base case in case of a list when we want to reverse it? Maybe somebody wants to type it in the chat, so we wake up a little bit. what is equivalent to 0 in the list, I would say. Okay, I see no educated guesses, so I'll just assume there are none. If the list is empty, then we should return the list itself. Otherwise, we're fine with this one. False. So they do not return the same thing. Let's see what they return. All right. Okay. I actually don't know why is there an external bracketing over here. Okay. We take the last element and then we just call it on the. Yep. Do you have an idea, Seb?
Yeah, I'm not sure. So if you just did L of -1, that would just take one element. So I'm not sure in Python you can append one element to one list with a plus. So you need to make it a one item list and then append that.
Yeah, that's what I did. I mean, this is a one element list, isn't it?
Yeah, that's what I mean.
Do you think it shouldn't be this way? I think it should be.
No. Yeah, no, that's what I mean. I thought you said I thought you wondered why the outside bracketing is required there.
No, I'm wondering why does it output incorrectly?
Oh yeah, right.
If you have an idea here, because I'm quite confused here.
Oh, you put don't you put there a doubly, like it's a nested list there, like at the print. Look at the argument.
Oh, of course. Wow. Good catch. Yeah, they're the same then. We can compare it. Great. Yep, they return the same thing. Okay. Let's now move to handling errors in Python. Yeah.
I think there's a quick question in the chat.
Okay. Okay. So first, -1 is the last element of the list. I think we already mentioned it, but if you want to take the last element from a list, then you can index it with negative numbers, starting from 1. Whereas this -1 is that we don't take the whole list any longer. We just take all elements except the last element because we already prepended it. We already put it on in the front. Does it answer your question? And are there any other questions regarding functions or recursion? Because we're now leaving this topic. Okay, then we'll go into handling errors. Last 3 terms are ignored. Okay. I don't really get the question. So would you mind unmuting yourself, Harvey? And just speaking up? No terms are ignored in the reverse function, if that's what you worry about. Okay. So coming back to handling errors, we'll just do the workspace. Okay, so in Python, when something doesn't work, the program will throw an error, sometimes called an exception, but errors and exceptions are fundamentally the same in Python. There are different types of errors in the language. So there might be the index error, where we want to access an element in the list that is not there. It usually means that we're accessing element that is, well, at the index greater than the length of the list. A key error exhibits itself in dictionaries, which we haven't done yet. A recursion error we actually seen today. So if we call the same function too many times, it will just shout at us to not to do it. Syntax errors are usually when we miss a bracket, not make a colon. So they are thrown at a different stage. So when our program is compiled, so it's read by the computer, it translates it to its own language, and if it sees that something is not really a valid statement, then it will throw a syntax error. So there are all those different types of errors. You can check them in the Python documentation if you see an error which you don't know or haven't heard about. And another things we can do with errors is raising them. So in this example, we want to access the nth element in the list, right? So normally it would also throw an index error, but here we want to be a little bit more explicit. So we just raise the actual error here. Right? So we can try, let's say, access L of, well, we have 1, 2, 3, and we want to access the 6th element. Yep. So instead of actually giving us information here, which it would normally do with, let's say, 1, 2, 3, and we want to access the 6th element, then it would inform us. Here it doesn't inform because it's our own raising of the error. And it will usually point us to the line where the error was raised. A neat thing which we can do with errors is to catching them. And catching the error means that we somehow control the execution of the program, even though the error will be thrown. So in this example, we want to convert string 10 into a floating point number. And we use the try statement. So we sort of suspect that A might not be a valid floating point string. And then we catch it by the except statement. So except takes the name of the error as the argument here, and it will, in this case, just print us a helpful message that there is a value error. Please use digits in your string. So if we do, then it will be fine. Otherwise, it will throw the value error. This is fine. This is not fine. Okay. Here are 4 basic errors. So I'll give you a minute to think about those. What could happen here? Let's say that when S is not explicitly defined, it was not defined. So what error would be thrown in all of these cases? Yep. Let's give it a minute. Okay. In the meantime, I'll answer Harvey's question. So Harvey is asking about this line. Okay. So this is the notation of the for loop. So first argument of the range is where we start. Second argument is where we end, which is not inclusive. So it's effectively 0. And the -1 here denotes that on each iteration, we'll actually decrease this by 1. On default, we usually increase. So this would be +1 if we were going from the beginning of the list. But now we're going from the back. So we know we need those -1s here. There is also the obvious way of reversing a list using the list functions. So let's say obvious, where L, where we just do this thing. Colon, -1. This also reverses the list. Okay, May actually wrote something. Great. Value, good. Might be a value, yeah. That's a good point. It can also be a name error, which I haven't mentioned, but name error basically means that this thing was not defined. So you can't just increment something that we don't know what it is. Index error, very good, because it's shorter than the index we require. What about C? Great. D is a bit more tricky. We can see that 2 to the power 5,000 is a very, very big number, and it causes something called the overflow. Actually, this number would be still evaluated, so I hope at least. Let's give it a shot. This is fine. What's tricky is that we want to. This is the notation of creating a list of zeros of given length. As you might remember from multiplying and adding functions. So we want to create a list. Okay, see you, Seb. This will be a list of length given by this number. It will be a very, very long list of zeros. And this is just too long, and it will cause the error called overflow error. So this array, this list, is just too big to fit, so it breaks. Okay. How about doing the second one? So it uses a pass statement. So pass statement, let's say we have an x given by 1, and if x is equal to 1, then I do pass, then it doesn't do anything. So it sort of ignores it. If it's 2, then it will just print the haha message. But what's important is that this pass just gets out of the if and continues the code based on what is later on. It might be useful in this exercise where we use the try catch and then a pass statement. Give it a maybe 3-minute thought, and then I'll do it. Welcome back, Seb. Okay. I will slowly start defining this function. So we have a list of many different things given. We have a list of a number, a boolean, another int, strings, and even a function. And now we will try to catch type errors. So result is equal to 0. And for lm in L, try res plus equals to which one? Yep, lm. If try fails, except type error, then we'll just pass. And we can do some numeric. Do you want guys to do the counting and see whether the sum is actually correct? We have 5, 6, which gives 11, and then plus 5, which gives 16. And we got a 17. Any ideas why that might be? You can unmute yourselves or put it in the chat. Yep, exactly. So true is given as 1. So this is the example where we have to be actually really careful with try and catch statements, because some things might actually pass in Python that we don't really want to pass. So true is counted as 1, which is the default interpretation of it in Python. But but we might actually don't want to add the true. So in this case, probably type checking would be the safer option, but as it was said in the specification of the question, we can't use the type function. So it's not fully functional. Booleans would break it. Okay, great. Any questions about handling errors? Yep, a very valid comment from Seb that Booleans are easily converted in C and C++ as well. Okay, if there are no more questions for handling errors, then we'll go straight into importing, which is the last part of our lecture today. So importing in Python is a pretty simple thing. We just have to know the name of the module we want to import. So for example, if you'll be working with some scientific environments, you might often find it useful to use some mathematical functions. And for example, sine is not defined in the basic Python library. So you have to import the math library and then reference by the dot that we want to call the sine function from the math library. If we wouldn't use a dot here, oh, it would work actually. But it might be that Jupyter Notebooks import some functions. Let's see if we can find the example where it will shout at me. Yeah. So for example here, when we use the randint function, if we don't do the random.randint, then it will shout at me that it's undefined. Well, quite unlikely. I got 100. Okay. So math has, for example, trigonometric functions, hyperbolic functions, probably lots of useful stuff. You can search, for example, math Python documentation. And you can see which functions are available, like ceiling, absolute value, factorial, floor, many useful functions here. If you want to play with those in your free time, then do not hesitate. Permutations, all of these things. If you don't want to import the whole library, so keep your files as small as possible, then we can import single functions. So in this case, I'm importing a sine, and I can call it straight away because Python already knows that sine will be the sine from maths library, so it's all right to call it straight away. If we don't want to do the dot notation, we can just import everything from the math library, which is given by the star. So it just says import everything from math module, math library. And now we can also call without the dot operator. I personally prefer denoting which library we're using, but if you want to keep it a bit more brief or for yourself, then go ahead. Okay, here's an example for a different library called Numpy, which is very popular. You might work on it in Python101. And here you can also give aliases to the libraries you're importing. So you use the as keyword to say that, well, I will call numpy and np for the sake of brevity. So I can call it a cake if I want to. And then I would have to do cake here. Like the same. But np is a very common name for numpy. There's also another way to do it. So if we want to import a specific function, as here we do. From math, we import something, and now we can even rename the function in the actual math module. It might be very useful in case we have two functions, one in the module and one defined by ourselves that are named the same but might do different things. So I might define as def sqrt function, which does something, I don't know, different, doubles.
Someone's asking what's the difference between the NumPy and the math libraries?
So they are just different libraries. Like you have many modules given by the community and developers that do different things in Python, which are not included in the basic Python. So NumPy is more scientific, working with arrays, matrices, multidimensional structures, whereas math library is more for analytic functions, let's say exponentiation, logarithms, and well, many functions, but mathematical functions. Yeah, so if you are looking to, let's say, use a hyperbolic ton function, then you would probably import a math function and then call it in your program, because you know that you need a mathematical function that might not be defined in the Python standard library. For NumPy, you might analyze some demographical data or some biological data in a big matrix. And in this case, NumPy might be useful. I hope it answered the question. Okay. And we do, let's say, return. sqrt will just increment it by 2 out of the blue. And now we can do sqrt 4. And it will actually use our definition instead of the math library definition. If we wouldn't do it, I'm wondering what would happen. Okay, so it would still prefer our local definition. But it's safe to change this name here. The last important library, or maybe the second last, is random. So random allows you to generate random pseudo-random numbers, but they are in a sense random, which allows you to get random numbers if you want to do some simulation. For example, given a uniform distribution of something, you want to see how a thing behaves. You might generate random numbers in a while loop, for example, and see how it works out. So for example, we might want to compute the average of the uniform distribution from 0 to 100. Then we do the average. We'll start from 0 and counter. Yep, and let's say while count is smaller than 1,000, then we do average plus equals random randint from 0 to 100, and then we return. the average divided by the count. So the number of elements we account into average. No, we don't return because this is not a function. But yeah. And then we print this, for example. Yep, so it's around 50. If we do 10,000, might be a bit more accurate. Yeah, we're getting more and more accurate. Now it takes a while, but yeah. So for 1 million operations, it takes a little while, but we're getting closer and closer to the actual thing. Yeah, and other libraries that that Seb mentioned, which is a really good comment, is SciPy, Pandas, Matplotlib. These are really useful. So Matplotlib is used for plotting. So if you want graphs, or if you want like to show something graphically, then it should be there. We can actually have a look. I think it's also on the web page. Intro to Python. Yeah, there is a tutorial on plotting graphs in Matplotlib, so you can plot nice graphs using Matplotlib. I don't know if SciPy is still used that much. You'll have to verify it online. I don't think it's that popular now, but Pandas is also a really great tool. So this is Matplotlib. You can even make a moving ones. And Pandas, we have a whole separate module about Pandas. So if you want to analyze databases, then Pandas is a good way to start. I'll put it in the chat actually.
I want to actually add a thing, because this has been my home subject, which I did at my internship. These kind of 4 libraries are actually what the libraries that supercharge Python so much that it dwarfs like MATLAB, because it's just as good and free, which is why a lot of people gave up MATLAB.
Yeah, MATLAB is strange, but yeah, thank you for that. Yeah, so if you have any comments or ideas or anything in principle, then please shout out now. Yeah, this is a wrong subtitle, but yeah. Anyway, next week we will be working. I'm not sure about what. I'll check. Yeah, I'll do it on my drive actually. I'll show you the curriculum. Yeah. So next session we will be working on tuples dictionaries, some control flow statements and sets, and also plotting. We'll do something in Matplotlib, some basic plotting if you want to delve into it. But yeah, other than that, we're done for today. The session was a bit shorter. But yeah, thank you for your attendance. And if you have any other questions, please do not hesitate to ask me.
Okay, someone's saying if you could upload the workspace before the session. Yeah, I mean, I'll speak with Lukasz and we'll try to put that on the Facebook event beforehand. Yeah, and we'll also on the Teams. Yeah. All right. Yeah. Thank you so much for that suggestion.
Great. Thanks a lot, mate.
Yeah. Okay. Yeah. Thank you, Lukasz, for this. You went well. Thank you.
Thank you, Seb. It's a really nice one. Okay. Yeah. Okay. Thank you, guys. Hopefully, I see you next week. And yeah, if you have any questions, you can. I'll be here for a couple of minutes if anyone has any questions. If not, then see you.